Sylow's theorem says that if a prime p has a power, p to the k, that divides the size of your finite group, then your finite group must have a subgroup of that size, p to the k. So let's see what this means in an example. Let's consider D6. D6 is the set of, or the group of rotations and reflections of a regular hexagon. So here's a hexagon. We'll let rho denote the clockwise rotation, and we'll let alpha denote reflection about an axis. So D6 is the group containing 1 rho, rho to the 5th, alpha, alpha rho to the 5th. The size of D6 is 12. 12 elements in the group. 12 is 2 squared times 3. So Sylow's theorem says there has to be a subgroup of size 2, there has to be a subgroup of size 2 squared, and there has to be a subgroup of size 3. As for subgroups of size 2, a subgroup of size 2 has to be a cyclic subgroup generated by an element of order 2. Alpha has order 2. If you reflect twice, you get the same configuration of the hexagon back. So the cyclic subgroup generated by alpha is a subgroup of size 2. And it turns out there are more elements of order 2 in D6. In fact, there are 7 of them. You could have alpha rho, or anything of the form alpha rho to the power. All of these elements, all 6 of these elements happen to be order 2. And additionally, rho cubed has order 2. So there are 7. Sylow's theorem also says there are subgroups of size 2. So here's one of them. It's the subgroup generated by alpha and rho cubed. So this is the notation for the smallest subgroup that contains both alpha and rho cubed. So it's all possible products of alpha and rho cubed that allow you to get a subgroup. And this is a 4-element group. In fact, this is the group 1 alpha rho cubed and alpha rho cubed. Order 4. There are more order 4 subgroups as well. There's the subgroup generated by alpha rho and rho cubed, and also alpha rho squared rho cubed. So there are 3 subgroups of size 4. 3 is also a prime that divides the size of the group. So Sylow's theorem says there has to be a subgroup of size 3. There's only one of them. It's a subgroup generated by rho squared. So some of these subgroups we'd like to study in further depth. The subgroups that will involve Sylow theorem number 2 and 3 are the subgroups that correspond to the highest possible prime power. So let me make a definition. A Sylow P subgroup of G is a subgroup of size given by the highest power of P that divides the size of the group. Here P is prime, and the size of the group is finite. In fact, when we're studying the Sylow theorems, that's going to be going without stated from here on out. P is going to be prime, G finite. So that's a Sylow P subgroup. So in the example of D6, the Sylow 2 subgroups are these 3 subgroups of size 4. The subgroups of size 2 are not Sylow 2 subgroups because 2 is not the highest power of 2 that divides 12. So the Sylow ones, the Sylow 2 subgroups are these guys, and the Sylow P subgroups are these. So that's the definition of a Sylow P subgroup. It's a subgroup that corresponds to the highest possible power of P that divides the size of the group. A Sylow P subgroup must exist. That's the content of Sylow theorem number 1.